And I just would like, starting my presentation, to give you an example, a couple of examples that show that still we have to learn much about water. We experienced in Italy last autumn a series of floods that were really very concerning for us because we had losses. Many people lost their lives, and the reason was clearly that they were not prepared to deal with the flood. They were really very quick floods. We call them flash floods, rapidly evolving. These people were walking in the streets, and they noticed that the water came in the street and was rapidly increasing in level. But still, they tried to get back the cars from the street. They tried to save material things that were kept in the houses. And in the video, we could see that people was trying to drive out from a street that was being flooded. And clearly, they were not prepared to deal with this event. They didn't realize that water is extremely dangerous when it flows quickly. We have to realize, people should realize, to give to you an example, that when we get in the water until this height and water flows quickly, it's almost impossible to keep the equilibrium. And these people were not prepared. So we learned in Italy just some months ago that we have to really prepare the population to deal with water. And this was a first example. And let me give a second example that shows how much we still have to learn about water. And this is the example of the Lake Harald disaster. This is probably one of the worst ecological disasters caused by humans. And the disaster is summarized in this picture. You can see here a picture on the left of the extension of the Lake Harald in 1989. And after only 14 years, you can see how much the extension of the Lake Harald was reduced. Lake Harald almost disappeared. And the reason for this was not just climate change. The main reason was that in the former Soviet Union, they decided to invest a lot of money in the cultivation of cotton for economical reasons. But cotton needs a lot of water. So they started to take the water for irrigation from the Lake Harald and from the rivers that flow into the Lake Harald. And the result is that the lake is almost depleted. And this disaster is irreversible because the reduction of the lake surface caused a reduction in evaporation and therefore local climate change. So now this area that was covered by a lake looks like a desertic area. You see boats lying on the sand. This clearly indicates that we still have much to learn about these processes. But unfortunately, humans only recently started to study water. And to prove this fact, let's say that until 1600, so until about 400 years ago, humans didn't understand well from where water flowing in the rivers came. They thought that the main contribution to the river flow was coming from the underground, not from rainfall. They didn't realize until 400 years ago that the main contribution to river flow was rainfall. The reason for this is easy to understand. At that times, there were no communication means, so sometimes people got flooded without seeing any rainfall, and they didn't know that the rainfall was somewhere else. So they thought that the water was coming from the underground. It was only around 1600 that an Italian abbé, Benedetto Castelli, understood that the main contribution to surface water bodies was rainfall. And he understood that because he was able to relate the level in a huge lake located in central Italy, the Lake Trasimeno, to rainfall. He observed rainfall, he observed the river lakes, and was able to connect them. But only recently we realized how much is important observing water-related variables, how much is important to observe rainfall and river flow. And the result of this, I had another movie and I removed it, I'm sorry. The result is that now we don't have long observations of rainfall, river flow, other water-related variable. Let's think about rainfall. We started to observe rainfall only in the oldest rainfall cities in the world. They started to observe it only in 1725 in Italy. And the river flow observation started about 100 years ago. So our knowledge of these processes is very limited to the recent past. 100 years is nothing for nature, of course, we know. And this is a big problem because we could understand much better climate change if we had longer records, but we don't have. So there is clearly the need to better investigate the water cycle. And this is a scientific issue. And the science that is studying the water cycle is hydrology. I'm using here a cartoon that I downloaded from the website of the United States Geological Survey. I highly recommend you to refer to this website because there is a lot of educational material. And this cartoon here shows basically what is hydrology. In a few words, hydrology is the science of the water cycle. Now hydrology has a broader view. It includes the study of the distribution, quality, and movement of water in the Earth system. But let's say in a few words that it's the science of the water cycle. And we think that we know the water cycle very well because we were taught the water cycle in the primary school when we were children. And let me summarize very briefly how the water cycle is structured. We know this, but let's remind it. And conventionally, the water cycle starts from the ocean, from where the water evaporates, and then water in the form of vapor goes into the atmosphere. In the atmosphere, thanks to the wind, water moves over the lands, and eventually it gets close to mountain where the water vapor meets cooler air and then condensates to form the clouds. And okay, here it is, the clouds. And from the clouds, water rains down, lands again on the Earth's surface, and then travels downstream back to the ocean. And we think that we know this cycle in full detail because it looks simple. But actually, if we look at the single processes, we realize that things are much more complicated. Let me show you a more detailed cartoon here, again from the website of the United States Geological Survey, USGS. You see that things are much more complicated. Let's concentrate on the processes that take place over the Earth's surface. There is a first important process. When rainfall lands over the Earth's surface, part of the rainfall is kept by the vegetation through the leaves. This process is called interception. And then the intercepted water goes back to the atmosphere through evaporation. This is an important process. It has been shown to be very important also for preventing floods because a very important part, significant part of rainfall is kept by interception. Then the rainfall that survives interception reaches the ground, and there is another important process that is taking place, infiltration. Infiltration means that part of rainfall goes into the soil and then forms the groundwater discharge and the groundwater storage. There is a flux of water that in the underground goes downstream. And the difference between groundwater discharge and groundwater storage is just the velocity of the movement. We call it groundwater discharge when the velocity of the movement is significant. When instead the movement is very slow, we talk about groundwater storage. There is a part of water that does not infiltrate and flows over the Earth's surface. It's called surface runoff and contributes to the formation of the river flow. And then we have these two types of flows that go downstream in a very complicated way, because in rivers we have turbulence, and we have also a continuous exchange between groundwater and surface water. Part of the surface water infiltrates, and part of the groundwater comes over the surface through the springs. And also snowmelt processes are very much important, especially, of course, in countries where they rely on snowmelt for water supply. All these processes are very complicated to describe, and if we look at the oceans, we have a couple of processes again more than a couple, but let me concentrate on a couple of processes that are very important. First of all, we have a direct flow of groundwater direct into the oceans without passing from the rivers, which cannot be observed because, of course, it's underground. And also we have the streams in the oceans that are very much important for governing the climate. Water is part of the climate, of course. Now, let me concentrate just to give you an idea of the complexity of the processes on three issues. Three, let's say, scientific questions. And the first is how rainfall partitions into infiltration and overdam flow. So how it gets divided between water that flows over the surface and under the surface. Second question is how does groundwater flow take place? Third question, what is the amount of direct fluxes of spring water, groundwater, into the oceans? Let me go into more details into these three questions. Just to give you an idea, these are three very important processes. First, how rainfall partitions into infiltration and overdam flow. I would like to explain to you a theory. It's quite technical, but I think it can be explained very simply. This is an animated picture that is looping. So while I'm talking, you can see the picture describing what I'm talking about. This is a theory that was formulated about 100 years ago. It's called Ortonian mechanisms, from the name of the scientist Robert Orton. And it's also called infiltration excess theory. Accordingly to this theory, rainfall, when it gets over the ground, gets subdivided in two components. One component is infiltration, as I mentioned before, and the second component is overland flow. Infiltration contributes to the groundwater storage and increases the level of what we call the water table. The water table is, it's here, it's the roof of the groundwater storage. And therefore, the water table is continuously changing its level depending on this process of infiltration. And then, as I said, the overland flow forms the flow into the rivers. This theory was recognized to be not fully appropriate in many cases because actually, what is called overland flow, we cannot observe it. If you go over a field during a very intense storm, you can't see water flowing over the ground. But you see the water level in river increasing. So it seems that this theory is good enough for very steep hill slopes and for impervious areas like the roofs of our houses, but it's not very much appropriate in this case. So hydrologists devised an alternative theory. Let me show to you a sketch of the second theory, which is called saturation excess, or also Danyan theory, Danyan mechanisms. Accordingly to this theory, rainfall, once it gets over the ground, infiltrates, totally infiltrates. So rainfall, all the rainfall infiltrates and increases the level of the water table. By increasing the level of the water table, it may happen that the water table gets to the surface of Earth, so generating the presence of saturated areas. You see here, this area here is saturated. And then if it rains over the saturated area, then the overland flow is originated. This is a different theory. And the way in which these two mechanisms combine to form what happens in nature is not clear. Hydrologists are still making a lot of experiments, and I will show you some pictures later on, trying to understand what's going on. What is the prevailing mechanisms? Okay, let's now move to the second issue. How groundwater flows. And let's look at the first cartoon here. You see that the water bodies in the underground are more than one typically. We don't have just one water body in the underground. We have several layers. Typically, we have the first layer, the first water body, which is closed to the Earth's surface. And typically, we call it unconfined aquifer. Unconfined because it means that the water table, the roof of this aquifer, is in contact with the atmosphere. There is no barrier above. So we call it unconfined aquifer. And what is very much interesting to note, I think, is the time scale of these aquifers. Time scale, I mean the time that is needed to completely replace each aquifer. So if I say that the unconfined aquifer has a time scale of days to years, it means that we need days to years to completely replace this water. If you go in deep, in more deep, you see other aquifers which are typically confined, meaning that they are within two bedrocks, and the time scale increases. And if you go very much deep, the time scale can take millennia. This means that if we exploit this water through wells, and we go to very deep aquifers to take the water, the perturbation that we induce can last for millennia. So the consequences of our action can last for millennia. So we have to be very much careful when we take groundwater. We have to be very much concerned about the time scale of the aquifer, because otherwise we could induce a non-sustainable situation where we take the water and then when there is no water anymore in the aquifer, it takes millennia to get re-established. And this highlights the importance of studying the human impact. But I will talk about this later. Third question, direct flow of groundwater into the ocean. It's not possible to quantitatively estimate this direct flow. We can get an idea, but we cannot observe it, so to obtain a good estimate is not possible. There are people trying to set up global mathematical models, global meaning extended to the whole Earth, to understand these fluxes. They got an idea, but they are still not able to quantify them reliably. So the moral of the story is that we don't know these fluxes, but these fluxes have been proved to be extremely influential on ocean circulation. For instance, the Gulf Stream is very much influenced by these direct fluxes of groundwater into the oceans. So the moral of the story is that if we don't understand these fluxes, we cannot model the climate system reliably. There is uncertainty. So it seems that the picture that I'm giving to you is skeptical, is a pessimistic picture, because so far I just said that there are many things that we don't know. But indeed, I think this is a very exciting situation. In science, when there are things that we don't know, there is a lot of excitement. And in fact, hydrologists are very much excited, and I have to say that hydrology is a very excited community, very stimulating community with many young people, and they are very much motivated to understand more and to make experiments. And let me give you some examples. What hydrologists do to try to solve these problems. First of all, the topical research field, one of the topical research field is the study of the drop paths. The ways the drop follow to reach the water bodies, because we still don't know these ways. So hydrologists are using tracers to try to understand what is the way that the drop follow. They typically release tracers in the catchment, and then they look at water bodies, and they look when the tracer get into the water bodies. Don't be concerned about the fact that the tracer is red here. It's not a pollution. It's just, sometimes we use salt, for instance. So it's not a pollution. It's an exciting field of experimentation. And there are a lot of groups, of the research group, that are investigating this issue. Second issue, to understand how interception works. So many people are doing experiments under the trees to understand, to relate rainfall with the part of rainfall that reaches the ground. And here they are trying to estimate the water flow along the trunks, along the branches and the trunks of the trees. This is an important contribution to infiltration. You see they are measuring here and here the water flow along the trunks. And here they are measuring soil moisture and rainfall and so forth. Another interesting research, another interesting research area that is relatively new is the study of the human impact. And this research area is called now socio-hydrology. It was just launched, and the initiative was taken by Professor Savenay, Sivapalan, and Bloch that are sitting in the room. And this is extremely important. Look at this picture. This is a picture that was taken in Warsaw in 1995. The next picture showed the same place 8 years later. Look at the wall here, because it's still there in the picture, but the only thing that you can recognize in the next one. You see? This is a tremendous impact. And it's important to understand one basic thing. This impact is concerning for two reasons. First, the effect on the water cycle. Urbanization is affecting the water cycle, of course. But it's also concerning because we have to give water to these people. So there is a relationship between water and people, and a feedback relationship between people and water. So it's a two-way interaction that we need to study. And socio-hydrology is extremely important because it's trying to understand these processes and also the processes related to groundwater exploitation, as I mentioned before. And also another important issue is irrigation. Irrigation is causing what we call a blue to green water diversion. Means that the water is taken from the river, the blue water, we call it blue water, and is used for irrigation and therefore evaporates. So it becomes green water. So there is an increase in evaporation. The total mass of water doesn't change, but there is a change of status from the liquid status to the vapor. And the problem is river depletion, because there are many rivers in the world that are getting depleted, like the Colorado River, the Yellow River in China. There is almost no water reaching the ocean in these rivers because they are fully exploited. And this is a human impact that is extremely important. Look at this picture that is trying to devise the complex interaction between water and humans. And this interaction at the end is extremely important because we need to secure water for people. And as I said at the beginning of my talk, water scarcity is becoming a relevant issue. And so let's have a look at the numbers. How much water do we have? It's impossible to read these numbers. Just to give an idea, on the website of the USGS, you can get an estimate of the total amounts of water and the different forms in which you can find water. Let's have a look now at a graph which is easier to read. If we look at the total global water, we observe that 97% is salt water, so it cannot be used for human use unless we desaline it. Of this 3% of fresh water that is available for human use, if we explode this 3%, we find that about 70% of the 3% is in the ice caps and cannot be used. About 30% is groundwater and 1% surface water, about. So you understand the importance of groundwater. We need to use groundwater, but to use groundwater is extremely delicate for the reason that I mentioned before. If we look at surface water and explode this 1%, 1.3%, we see that snow and ice is about 70% of this 1%, and lakes have an important contribution. Rivers are only a small fraction. This is a problem because it's very convenient to take water from the rivers, because rivers flow almost everywhere, not everywhere of course, but almost everywhere, and it's very convenient to take water from them. Global water uses. Look at the dramatic increase of the global water use in the past century. And look at the fact that, in particular, Asian countries have increased their water use, which is good, because a higher water use means a higher societal benefit, and therefore it's good, but it's also concerning. And let's have a look at how this water is used. And you see that, of course, we are increasing, but agriculture is using the major part of water. And this is known. If you make a ratio between the water used for civil use and for agriculture, it's about 1 to 10. 1 to 10 in many countries. So we have to be concerned about agriculture and industry a bit. Are these uses sustainable? Let's have a look at an example. I'm going toward the end of my talk. The example is the Po River in Italy, which is a very important area because about 40% of the gross product of Italy is produced in the Po River Valley. And if you look at this number, not individually, but let me concentrate on the groundwater recharge concerning issue, as I said. We have estimated every year a recharge to groundwater of about 9 billions of cubic meters of water, which seems to be good, but if you look at the amount of groundwater withdrawal is close to the recharge. So this is very much concerning for us. And it means that we cannot take more water from groundwater in the Po River Valley. And this means that probably with the population density, we are getting close to a maximum if we want to rely on our own water, because water can also be imported, maybe virtually. This is another story. So this picture shows that the situation is still sustainable, but the margins to ensure sustainability in the future are limited. And let's have a look at a global view. In this graph here, you see for many countries, and I put in red the most important one, Vietnam, Philippines, India, Japan, Indonesia, Brazil, Congo, United States. You see the population density, inhabitants per square kilometer. This is quite easy. And also you see here the total amount of fresh water availability. These are public data, are available on the web. And the question is this fresh water availability enough for the people living in these countries? The fresh water availability is given in kilometers square, in cubic kilometers per kilometer square. So is this fresh water enough? Of course, the reply to this question depends on two things. The efficiency of the country to exploit fresh water, what I called here A, and second, the water needs. So if a country is very much efficient, then it can use higher water needs, and also it can increase the population density. So let's show in the picture here the situation of Italy. So the situation given by water use efficiency in Italy and water demands in Italy. And of course, the fresh water demand depends on the population density. So let me show here the situation of Italy. You see that Italy is matched. And this blue line shows to you that countries that are located below this blue line have a different situation. They are suffering with respect to Italy. It means that either they are more water efficient or they have to reduce with respect to Italy the water demands. And this is the situation of Italy, but Italy is quite efficient in using water. If you draw a different line for reduced water efficiency, you see that the situation is a bit concerning. There are many countries that are suffering. And this is indeed true. We know that many countries are experiencing water scarcity. So it means that either we increase water use efficiency or we reduce the water demands. Otherwise, water will become shortly a limit for the development. Population density cannot increase if there is not enough water. The water is being recognized now as one limit to sustainable development. Okay, so now there is also the climate change issue. Here you see an animated GIF from Wikipedia of the extension of the ice cap. You see that the extension of the ice cap is dramatically reducing. This is a clear sign of climate change. And also you see a proxy of solar activity, which shows that the solar activity is increasing in the recent past. These are two different proxies. And they show that, indeed, we are experiencing now a period of very intense solar activity. This is one of the possible explanation of global warming. And climate change is potentially much influential, no matter about the attribution of climate change. We can attribute climate change to solar activity or increase the CO2 concentration. This is not very much relevant to us for now. What is relevant is that temperature is increasing, and there is no doubt on it. And therefore, this is, of course, causing changes in the distribution of water. The total amount of water in the Earth doesn't change, but the distribution changes. And this is a concerning issue. Conclusion. Now, hydrology is a young science. Many of the processes of the water cycle are still not known, but hydrology is a very fertile science. It's a community, of course it's my community, so my opinion is biased, so you shouldn't listen to me, but it's a community that is very much motivated, very young, and a lot of ideas are going on. Really, I think it's an exciting field of research. Again, I am biased. We need more focused research, and to do more focused research, I'm a bit, okay, taking the water for me now, we need to recognize that water is a priority. Water is really a priority, and is a priority no matter of climate change, is a priority even now, and therefore we have to focus on this priority much better. Climate change, of course, is related to water and conditions water availability, so the study of climate change is extremely important. And now my final conclusion, every one of us needs to better learn about water. And especially we as teachers, we have to recognize that only an increasing public awareness of water dynamics can improve our efficiency in using and planning water use, in using water and planning water use. We need to gain a better knowledge from the public of water-related problems, water savings, water uses, because we strongly need, starting from now, to better optimize our use of water. Please help us to spread water knowledge among the public. That's all. I thank you very much for your attention.